everybody, welcome back. So in this video I'm gonna start by considering two functions, both two-dimensional. And suppose that there's some relationship between the two. I write that like this. U is going to be the solution to a PDE that we'll encounter later on, and what V is, I'm going to explain what that is later as well. And why we're considering phi equals 0, just bear with me, it'll become clear later. But for now, I'm going to take the derivative of both sides with respect to x. If I do that using the chain rule, I get this. And the derivative with respect to y, it's going to be the same thing, but instead of x here and here, I'm going to have y. My aim now is to eliminate the partial derivatives of phi from these two equations. I'm going to solve this first equation for partial of phi with respect to v. If I do that, I get partial of phi partial of u times partial of v partial of x equals negative times partial of v partial of x. So I'm going to solve for partial of v by dividing both sides by negative partial of v partial of x. So I get negative 1 over this times partial of phi partial of u times partial of u partial of x equals partial of phi partial of v. And now I'm going to substitute this formula here into the second equation. So this first term here remains as it is, plus, so I'm going to substitute this formula here for partial of phi with respect to v times partial of v partial of y equals 0. I'm going to multiply both sides now by negative partial of v partial of x and I'm going to divide both sides by partial of phi partial of u. Or I don't have to do that, I can just factor it. Doing so gives me this. So I'm going to write this this positive term here first. So partial of v partial of x times partial of v partial of y minus partial of v partial of x times partial of u partial of y equals 0. So by the zero product property, either partial of v partial of u equals 0, or this quantity in parentheses is 0. So I'm not going to make any assumptions about phi, so this being 0 is not a requirement. So that means that this quantity here is 0 in parentheses. Now you may recognize this this expression on the left side here. It is the Jacobian. It is the determinant of it's this determinant right here. So J, the Jacobian, is equal to partial uv over partial xy, and this is equal to 0. So what does this mean? So in order for there to be a functional relationship between u and v, the Jacobian of u and v must be equal to 0. So why is this important? Well, in principle, we can solve phi uv for u. We can write this. This implies that u is some function of v. This is useful because for PDEs of this form right here, we can write the solution as u equals arbitrary function of v. So u equals arbitrary function of v. So you may recognize this the problem of finding v as yeah, I said earlier that I was going to call v something, and it's the potential function. We're looking for the function v that satisfies partial of u with respect to y and partial of u with respect to x. If those are both equal to some given functions, we can solve for v, the potential function, and we can write the solution for u as a result. So let me be more explicit here. If I have a PDE axy, partial of u, partial of x, plus b xy, partial of u, partial of y equals 0. By comparing this PDE over here, I can say that u is a function of v, where v satisfies let's see, this is, so partial of v partial of y equals axy, and negative partial v partial of x equals bxy. So this involves finding a potential function v, and once I do that, I can write down the general formula for u. So the condition for which a potential function exists is if the mixed partial derivatives of v are equal. So v only exists if second derivative of v equals second derivative of v So basically the mixed partial derivatives have to be equal to each other for a solution for v to exist. And this this means that if I take the x derivative of both sides, this means that that partial of a, partial of x must equal. And now if I take the y derivative of both sides, this must be equal to negative partial of b, partial of y. That is, if I bring this both terms to the left side, I get partial of a, partial of x, plus partial of b, partial of y equals 0. This condition must be satisfied in order for this left side to be written as a Jacobian. So I think it's best if we work with some examples now to illustrate this. Alright, so to start off with, suppose that I have this PDE here, x sine y times the partial derivative of u with respect to x plus cosine y partial of u partial of y equals 0. So if we compare this to the form of a Jacobian, I'll write it down here so that we can compare. Minus partial of v partial of x partial of u partial of y. So I set x sine y equal to partial of v partial of y. And then negative partial of v partial of x is equal to cosine y. So does a potential function exist? Well, we can find out by finding the mixed partial derivatives of v. So doing that, I get the second derivative of v. This is equal to sine y. And second derivative of v, partial of y, partial of x, this is going to be just sine y. Because if I bring the minus sign over and then I take the derivative of negative cosine y, it just gives me positive sine y. So because these mixed derivatives are equal, there exists a potential function v that satisfies these two equations here. And that means we can write the general solution of this PDE, but we'll get to that later. But for now, I'm going to find v by integrating both sides of each of these equations partially. So for the first equation, I get v equals, so I'm going to integrate both sides partially with respect to y. So I get minus x cosine y plus a function of x. I'm going to call it h1. So, and now if I integrate both sides of the second equation partially with respect to x, I just get v equals negative x cos y plus h2 y. So looking at these two equations, I'm going to conclude that my potential function vxy equals negative x cos y. And that means that u is an arbitrary function of negative x cos y. This here is my general solution to this PDE, and it's all because the left side here can be written as a Jacobian if we could, because we compared it to the general form right here. So let's do a slightly more complicated one. Suppose that we have x plus 2y, partial of u partial of x, minus 6x plus y, partial of u partial of y, equals 0. So I'm going to compare it now to the formula of a Jacobian. Alright, so I set partial of v partial of y to the first term. And I set negative partial of v partial x to this second term here, so minus 6x plus y. I'm going to multiply both sides by negative 1 to get rid of the minus sign. Alright. So does a potential function exist? Well, we find out by finding the mixed partial derivatives of v. So differentiate both sides of the first equation with respect to x, and that gives me 1 because the coefficient of x is 1 here. And for the second equation, I'm going to differentiate both sides with respect to y. That gives me 1 as well, because the coefficient of y is 1. So a potential function does in fact exist. What is it? Well, we find out by integrating both sides of the first equation partially with respect to y. Doing so gives me the first term will be xy, and then plus y squared, and now plus an arbitrary function of the remaining variable x. And now for the second equation, I'm going to integrate both sides partially with respect to x. So the first term is going to be 3x squared plus xy, and then plus an arbitrary function of the remaining variable y. This first function tells me that v is xy plus y squared plus some function of x. The second equation tells me that v is 3x squared plus xy plus some function of y. That means that vxy equals 3x squared plus xy plus y squared. This unknown function h1x is just 3x squared, and the unknown function h2y is just y squared. And so I can say that the general solution for u is an arbitrary function of v, which is 3x squared plus xy plus y squared. So this is the general solution to this PDE up here. So this method here involving Jacobians is only for a very special kind of PDE, one where the left side is a Jacobian and the right side is 0. In the videos that follow, we'll learn about a more advanced technique that's much more applicable to PDEs. This is just a warm-up, if you will. So, I hope you enjoyed,